Okay, the schedule is quite delayed. I mean, we're supposed to have the last talk at 11:40, but it's already 11:56. So we're gonna move on quickly. So the next talk is given by Professor Shahar Kvatinsky.
Yes.
Okay, thanks. He's from Technion, Israel Institute of Technology, and his talk title is Real Digital Processing in Memory with the Memristive Memory Processing Unit.
Hi, thank you. Thank you. I'm happy that you stay. I'm the one that separates you from lunch. Hello to the ones at home. So I'm not going to talk about neuromorphic computing. I'm going to talk about something else. Maybe the only talk in the conference that is not about neuromorphic computing. I'm going to talk about digital processing in the memory, but I am going to talk about memristors. So I'm going to talk about how we can perform digital computation with memristors. And I'm sure that for this audience, I don't need to convince you that we need to do processing in the memory. Why doesn't it work? Okay, it's working now. So basically what I'm going to talk about is something that we call Memristive Memory Processing Unit. The idea is to perform digital computation inside the memory that is based on memristors. And the idea is to have a memory that has both the memory capabilities, and the CPU can access it just like any regular memory using loads and stores or read and write operations. But in addition to that, it has the ability to perform computation. So the CPU can ask the memory to perform also logical operations within the memory by describing the specific addresses where the memory is going to compute. Before I'm going to describe how we are going to do that, I just want to have some taxonomy, some categories for processing in memory, because this term is widely used for many different purposes. So when I talk about processing in memory, or when people are talking about processing in memory, they talk about moving the processing into the memory unit, but actually it has many flavors. So one flavor is to put processing units next to the memory array. And you can see this in this slide. But actually, this is not processing in the memory. It's processing outside of the memory, because we need to read the data from the memory array, perform the computation inside the processing unit, and then we need to store back the result. So that's like a CPU, but it's a processor inside the memory unit. So you can call it out-of-memory computation, and it's actually a von Neumann machine, but in a separate chip. A tighter integration of the processing to the memory is to use peripheral circuits for the computation, and maybe also use the memory cells for the computation. For example, neuromorphic computing, it's exactly that, right? We select the different rows and columns, and we accumulate current and sense it outside of the memory array using ADCs and transimpedance amplifiers. So we need peripheral circuits in order to perform this computation. So it's near memory computing. And it's not only for neuromorphic computing, there are many other ways to do that. For example, by scouting logic, where we perform digital computation, but we are using peripheral circuits in order to sense the result. In this talk, I'm going to focus about something different, which is using the memory cells and only the memory cells for the computation. So the memory cells will be used in order to perform the computation, and the peripheral circuits of the array are only used for control. We are just selecting the different memory cells that are used for the computation using decoders, for example, but all the computation, everything in the data path is inside the memory array. So this is real in-memory processing. And in this talk, I'm going to talk first about the fundamentals of the Memristive memory processing unit, how we are going to perform this such computation. And then I will describe a few applications that will benefit out of that. And at the end, I will describe a few of the challenges, because there is still a lot to do in order to make this completely functional. So let's talk about the fundamentals. How can we build a Memristive memory processing unit? So the first M is memristors. We will use Memristive technology Actually, we can use also other technologies, but Memristor seems like a very attractive technology for that. And when I say Memristors, I mean in the broader sense. It can be resistive RAM, it can be phase change memory, it can be MRAM, it can be STT-MRAM, it can be SOT-MRAM, doesn't really matter. Every technology has its pros and cons, but at the end, we can use any resistive memory in order to perform such a computation inside the memory array. I think that I can't move it.
Trying to hide that.
You probably can move it, no? Never mind. Just imagine the title. So we need memristive memories, and we are using the memristive memories to build the logic gates using stateful logic. And again, we can use also other techniques, but here today we will focus on stateful logic. So stateful logic is a logic technique where the memristors are used both to store data, because it's a standard memory, right? So they store information, but in addition to that, they also perform computation by serving both as the inputs and as the output. And also they are the logic gate itself, because everything is done inside the memristors. So basically, the resistance or the data that is stored inside the memristors can be the input, and the data that is stored at the end of the computation is the results. That's the output. And there are many techniques, stateful logic techniques. I'm going to focus on magic, which is something that we developed, but all the other techniques are valid as well. So what is magic? Memristor-added logic. We will see example of a NOR gate, but there are many other gates as well. Magic NOR consists of 3 memristors. 2 memristors are served as the input. So the initial resistance, the resistance prior to the computation, the data that is stored inside them, that's the input of the gate. High resistance means that it's 0. Low resistance means it's 1. We are using in a binary domain. Okay, we just assume that we have 2 extremes for the resistance, and of course we have more values, but we are just using digitize it in order to have zeros and ones, and so that's the inputs, and the output is the third memristor, which is its final resistance. The resistance at the end of the computation is the result, and again, if it's in high resistance, we are saying that the result is 0. If it's in low resistance, we are saying that the result is 1. And the way that we compute is with 2 steps. In the first step, we will initialize the output into the low resistive state, or to 1. And we will do it just like the way that we program the device in order to write in the memory. And in the second step, we will apply a voltage, VG, into one node, and we will put ground in the other node. And then we will have current that flows from VG to the ground. And because of the connectivity of the memristor, of the output memristor, it can either remain unchanged or its resistance can increase. And this condition, whether it will switch or not, depends on the inputs, because basically we have a voltage divider between the 3 devices. And based on the value of the inputs, we will either have high voltage or low voltage across the memristor, the output memristor, and this will be switch it or not. So this is basically the computation. So for example, if we had both inputs in logical 0 or in high resistive state, when we apply the voltage VG, most of the voltage will be across the high resistive state because it's a voltage divider. So across the output, effectively there will be almost 0 voltage. So it won't change its value, and it will remain in the low resistive state or logical 1. In any other input case, at least one of the inputs will be in the low resistive state. And now when we'll apply the voltage, at least half of the voltage will be across the output. And this will be sufficient to switch the resistance into the high resistive state or to logical 0, just like the truth table of a NOR gate. So this is a NOR gate. And similarly, we can build other logic gates. So for example, we demonstrated OR gates as you can see here in experimental results in collaboration with Professor Wasser from Jülich and Aachen. And here we demonstrated that in using the tantalum oxide resistive switches, VCM. So this is for an OR gate. And we also did that for other technologies. For example, a paper that was just accepted, we demonstrated phase change memories. So in phase change memories, the switching mechanism is a bit different. So the way that we are doing the stateful logic is a bit different. I don't want to go into the details, but you can see here 4 different gates that are experimentally demonstrated using phase change memory. And this is work that we did in collaboration with Professor Eric Popp from Stanford University. So we can basically do it for PCM. We can do it for resistive RAM. We can also do it for MRAM. So this is the basic logic technologies that we're using in order to build the Memristive memory processing unit. In order to do that inside the memory, it's not enough that memristors can perform computation, logic operations, but we need to do that inside the crossbar. So the idea is that all the logic gates will be crossbar compatible because we don't want to change the memory structure. The idea is to use this device both as a memory and also for the computation. So it must be crossbar compatible. And actually, if we look on the gate that I showed, and it's true for many other gates as well, you can see now that we have colors here in the different wires. And if you will follow the colors, you will see that actually this is exactly the same structure of a crossbar. So basically this gate is crossbar compatible, and just by selecting different columns or different bit lines in the memory, we can perform the computation. So we will select the different voltages that are required in order to perform the computation. And by that, we will be able to perform logic gates inside the crossbar. And not only that, we're also able to do that on multiple rows because we select different columns and all the rows are basically selected. So we can perform not only a single logic gate, but multiple logic gates, or it's a vector machine. We can basically perform a vector operation on multiple rows in one cycle. So it's not only that it's in memory, but actually it's a massive parallel machine. And this is only one form of parallelism. So we can perform the computation across multiple rows. Since the crossbar is symmetric, we can actually do the same thing across columns if we want. And in addition to that, we have other sources of parallelism because, for example, we can split the memory crossbar using partitions. And then we will have not only parallelism among rows, but we can have parallelism among partitions. So we can perform different operations or the same operations that we want using different partitions. So this is another form of parallelism. So we have even more parallelism than just among rows. And this is not the end. Actually, there is a third form of parallelism. And this form of parallelism is among crossbars, because in a memory, we don't have a single crossbar, but actually we have tens or hundreds of thousands of crossbars, which means that we can compute using tens or hundreds of thousands of crossbars. Each one of them have multiple partitions, and each partition has multiple rows, and it's all functions in parallel. So it's a massive parallel machine. So to conclude the fundamentals of the Memristive memory processing unit, we are using Memristors, using stateful logic, and it's all crossbar compatible. We're doing it inside the crossbar, and we have a lot of parallelism because we have parallelism between rows, we have parallelism between partitions, and we have parallelism between crossbars. And the last thing that I want to mention about the fundamentals of the mMPU is that it's very different than neuromorphic computing. And I will briefly say the differences, but there are some fundamental differences. First, neuromorphic computing is analog. Here it's pure digital computation. Also, neuromorphic computing accelerates just like the previous talk. It accelerates matrix vector multiplication. In the mMPU, we are doing logic gates. So we basically perform general purpose operations, and not necessarily matrix vector multiplication is something that we accelerate. And also, as I started, neuromorphic computing is near memory processing, while the mMPU is in memory processing. Also, The peripheral circuits are very different. In neuromorphic computing, we need ADCs and D2As. In the mMPU, the peripheral circuits are very similar to standard memory. We just need to extend the decoders in order to be able to select multiple rows and the ways that we select the logic gates. So it's very different. It doesn't mean that one is better than the other, but it means that they are very different processing in memory techniques, and we need to remember that and understand the differences. Okay, so in the remaining time that I have, and I'm sure that you are all already hungry, I will talk about a few applications that will benefit from that, and then I will just briefly mention the challenges because I want to leave you with an optimistic taste, so we won't talk about all the challenges that exist. Okay, so we know how to perform NOR gates or other gates. NOR is a complete logic family, which means that we can perform any computations that we want, right? So just by using a sequence, a set of NOR operations, we can perform everything that we want. We can do different logic operations, different arithmetic operations, and the arithmetic operations can be as complicated as we want. It just means that with the sequence will be long. So if we want to do matrix vector multiplication, it is possible with NOR gates, but it will take a lot of time, or the latency will be very long. If we want to do something more simple like multiplication, that I will talk in the next slide, then or in a few slides, it means that it will take a shorter time than the matrix multiplication. And with that, we can build this machine. So this machine will consist of multiple crossbar arrays. Each one of them is built in a crossbar structure. We are able to select rows and columns. And we have also a controller that knows how to translate a desired function into a sequence of logical operations. So for example, we want to perform some task for, let's say, addition of two vectors. So those two vectors are stored in the memory. And in a standard von Neumann machine, if we want to add them together, then the CPU will need to read the first element A0 and B0 from the vectors, perform the addition, and then stores them back into the memory, and then it will do it to the second element. And at the end, all the vector will be stored, the vector result will be stored inside the memory. But in the mMPU, we will do something different. What we will do is that the processor will send a command to the mMPU, to the controller. The controller knows how to perform the addition. It got from the CPU the addresses of A and B and the desired location for the result. And now it will split it into a sequence of NOR operations. So let's assume that it's 4 NOR operations. So the first step will be to select the rows and columns to perform the first set of NOR operations. And then it will perform the second set of NOR operations, including using the intermediate results from the previous one, and the same for the third one. And at the end of the fourth one, basically it will select as the output the location where we want the result to be stored. So at the end of the computation, the output vector will be stored inside the memory without the need to move the data outside. And with that, maybe I'll skip about that. And with that, we can perform. And with that, we can do basically any operations that we want. So for example, one of the things that we're doing is to find the right algorithms to perform efficiently inside the memory different tasks. So for example, one thing that is presented tomorrow in a poster by Orion that is here is how to perform all the arithmetic operations, subtraction, addition, multiplication, division, using the mMPU. And not only that, it also supports different data representation, fixed point and floating point. You should understand that they are very different when we want to perform arithmetic operations. For example, one of the challenges is when we want to perform an addition in a floating point, then there is a need to normalize the mantissa because of the different exponent values between two numbers. And if we want to do that in parallel on multiple numbers or multiple rows, then the normalization or the shift that we need to do in order to normalize, the shifted amount will be different. So we can't just give the same task or the same operation among all rows. So one of the things that we proposed in this work is how to do that in parallel, how to support different shift amounts and not losing the parallelism. So by that, we can accelerate the operation by orders of magnitude. And you can see in this table by how much we improved the previous algorithms for each one of them. And you can see that it's 1 to 2 orders of magnitude compared to prior work. So if you are interested in that, go to Orion tomorrow to this poster. And since we are able to perform arithmetic and logical operations inside the memory, we can run different applications. So a few examples of applications that can be used in the mMPU. One is image processing. You can see here in this graph, improvement in the throughput, in the speed of performing different tasks in image processing compared to different accelerators. And you can see that it can be, again, 1 to 2 orders of magnitude faster than accelerators. Another example is deep neural networks that can also using floating point operations. This is work that was done not by our group, but it's a paper that they published in ISCA 2019, and they show that using MAGIC and the mMPU, it is possible to perform training of deep neural networks faster and more energy efficient than a GPU. Using a RIT-PIM, the techniques that I showed before, we can actually improve the arithmetic operations that are required, multiplication and the addition, quite substantially, based on relative to those results. And another thing is DNA sequencing. In DNA sequencing, we need to compare long sequences, like long strings that have only a dictionary of 4 characters, because in the DNA we have only 4 possible characters. And using the mMPU to do that, we can also improve the different steps that are required. So in the first works that we did, a paper called the Field PIM, we accelerated the step of filtering the possible matches inside the DNA. And you can see in the graph, this is the latency, so lower is better. And you can see here that if we have more than 200 crossbars, which is a very low number, we can improve it compared to CPU. And with 10,000 crossbars, which is again not a large number, we can improve the latency by a factor of 100. So it's 100 times faster than a CPU to perform the filtering inside the memory. And now we are investigating on how to accelerate the entire pipeline of the DNA sequencing inside the mMPU. The last application that I want to mention is databases. So this is something new that we are doing. In databases, you have a lot of information, a lot of data stored inside the memory. And every time we have a query that is looking for some information inside the database, and basically it can be located everywhere. Sometimes it is actually looking for a lot of records inside the database. And then we need to do something with that, usually some simple arithmetic operations. And you can see here some results that we have for different databases benchmarks. On the top, you can see TPCH, which is a commercial benchmark for relational databases. At the bottom, you can see SSB. At the bottom, you can see comparison to MonetDB, which is basically a von Neumann machine, but that is dedicated for a real machine that is dedicated for databases. On the top, for the TPCH, we compared it to a commercial machine that its cost is $400,000 just to accelerate and perform a TPCH, because there are like known tests for that. And you can see that we improve by factor of 5 to 10x compared to those machines because of the massive parallelism, and mostly because we can reduce the amount of reads that are required. We perform a lot of tasks inside the memory, and then the amount of data that needs to move to the CPU is substantially lower. For example, in the top here, we reduce the amount of reads by a factor of more than 99%. And this is the main improvement. So before I will conclude my talk, I just want to briefly mention a few of the challenges that exist. So there are many challenges, of course. Not everything is bright. There are, for example, errors that exist. For example, soft errors. Soft errors is something that you can also, if you are interested, You can see tomorrow also Jan will present a poster about his work in ECC, error correcting codes, and how to have redundancy in order to improve the reliability when we compute, because sometimes the computation is not the computation is not perfect. So sometimes we get the wrong result, but we don't know that because everything is done inside the memory and we don't read the result. So we need somehow to compensate on that. Another challenge is the endurance, hard errors, because Memristors don't last forever, but computation can be massive, and we need the machine to function for a long time. Power is a limitation. We want massive parallelism, but at the end, more logic gates means more power. So we have a power budget, and we need to compute with massive parallelism with this power budget. And also the interaction between the software and the hardware. This is a fundamentally different architecture than the von Neumann architecture. It means that the software must be changed, because the software for many years is built assuming that memory only store information and don't compute. So that's another thing to consider. And as I mentioned, many algorithms can be changed because the computational model is different. So we can also redesign different algorithms. So to conclude the talk, we saw how Memristors allows us to build a non-von Neumann machine using digital computation, real digital computation inside the memory. And there are many aspects to that. From the physical side, make this work using and building the logic gate with the Memristive technologies. And I showed PCM and resistive RAM, but that's just two examples of technologies. Up to the software and all the middle algorithms, circuit design, all of that need to be considered. And that's what we basically are doing in my group. And in order to do that, we have a large group of talented people. Orion is one of them, but you can see all the others. And if you are interested in that, so tomorrow there will be also a poster by from Minui, which is actually about neuromorphic computing or security of neuromorphic computing. But we have a lot of people that are working on the different aspects in order to make it work. Thank you.
Thank you very much for the nice talk. Is there any questions from the audience?
Let's them eat.
Okay. I mean, if not, can I ask you a question?
Sure.
So if you go back to page 14.
14. Yes.
So when you do this computation, what happens to all the devices that's floating here? I mean, the rows
okay.
and columns floating there.
So basically, in order to isolate the devices, there are several techniques. First, we can put similar to a half right, like half select in a write operation, that you put half of the VDD. So it's not half of the VDD, but you put some voltage. We have some equations to find the right voltage in order to isolate the devices. Okay. And of course, you also can use selectors, for example, or transistors in order to deselect cells. It's completely compatible with 1T1R or any other architecture.
Oh, I see. Okay. So, I mean, the other question I have is that what's the ultimate kind of advantage you are seeing in this technology? So is it power, speed, or area? I mean, what's the kind of advantage over the existing technology?
So I think that the main advantage today is speed. Because of the parallelism, because of two reasons. One is parallelism, and the second thing is the reduction in reads. So we are looking on applications where conventionally you need to read a lot of information because you don't know, for example, databases, you don't know where it can be. So you need to look for everything. And the reduction in the number of reads, this is what gives you most of the throughput. Mm-hmm. Usually what we're doing, since basically in theory, the parallelism is infinite, right? Or the size of the memory, but the power is the limitation. So we actually set a baseline in the power to be equivalent to the baseline, to the normal machine. So in power, it's the same power.
Okay. Okay. Any other questions? Okay, let's thank the speaker one more time, and then I'll conclude this session. Thank you. Thank you very much.